Hello, everyone. Can you hear me? Yes. Let me do a show video and chat box. Thank you for responding. Hey, welcome to week 12, lecture B, and happy Friday. So today I'm going to help you to recall what we did last time. So if you click our playlist of our course, here you are going to see all recorded in here. And if you click 12a, and you are going to see what we learned. Can you hear me right? Last time. Okay. So we talked about digital control basics, ADC, DAC, discretization, sampling period TS, first order, high order difference equations, Z transform, properties, initial value theorem, final value theorem, and so on and so forth. Today, we are going to, starting from the Z transform and quickly go through that. After that, we stopped last time at a discrete convolution. So we used the definition here. You have a sequence. So it's from minus infinity to positive infinity. Then Z transform, if it exists, okay, converges. This may not converge, okay? So there's a domain of convergence, remember. So in this case, we use a very simple step signal and try to solve that. We did this one. So this is also called discrete integrator. And then this is a decaying signal. And so compare those to the low pass filter, okay? Inversion, we don't usually do according to the formula. We use lookup table approach. So there are two ways. One is to do the long division. Another one is to do the PFE, right? Partial fraction expansion. So basically, you can decompose it into the basic units like this, okay? Then you look up table, you get it. So properties, linearity, time shifting. So Z itself, it's a shifting operator. Minus K0 here is a Z to the power of minus K0. So that's a shifting, okay? So one-sided, then we have to consider where we started, initial condition. We should take care of it. So one-sided definition is from 0, so we need to be careful about our initial state. So then we talked about this initial value. So say, for example, we remember have if F and capital F are Laplace transformation pair, then F dot is S times Fs, then minus the initial value. So the same thing here, we have the initial value, but we have a Z in front, okay? We have a Z in here, be careful. So this is the initial values theorem. So you just simply send Z to infinity, nothing else, okay? Just X Z. But if you do a final value theorem, you send S to 0. This is for continuous time. But for discrete time, you need Z minus 1 times XZ, then send Z to 1, okay? Send Z to 1. So we can do verification of those two. We already worked out through the definitions. So we verified X0, X infinity are all correct, okay? So this is something we stopped last time. Let me do this. Let me remove all those nodes. We're starting from here, okay? So so we're here. Today, actually, we start from here. So this is a very important property. So remember, last time, when our input signal is a U bar, is a constant, then you can pull out the U bar outside. What if you cannot? So we do derived this form previously, when the u are different, it's time varying. Any type of function is time changing function. So what we get is different power in here, a to the power, different alpha to the power of k minus 1. We observed that the power and this index add together is k minus 1 always. See, k minus 2 plus 1 is k minus 1, okay? And so on and so forth. So this is actually alpha to the power of 0. So 0 plus k plus 1 is still k plus 1, k minus 1, sorry. So I'm trying to use, assuming everything is 0 when k is less than 0, so it's one-sided, okay? So for now, let's assume the initial condition is 0, okay? So we can write down the k, let's replace k with n. So alpha to the power of n minus 1, okay, and u0, and here we can keep going, okay, then until you have n minus 1, okay. Okay, so you can see that everything is, so because this is 0, okay, the x0 is 0, we can ignore this term, only take care of this one. If I write this without the initial conditions, so in a compact form, it's like this. Beta is constant. You can move the beta in front either, but this and this add together will be n minus 1. Okay, like what I said in here. Okay, so this is a compact notation, a sigma from 0 to n minus 1. Okay, n minus 1. All right. So this one actually, we assume this whole thing. So I copy uj in here. This is uj is the same as u sub j. We copy this one as, this is a definition, as alpha to the power of n I minus 1 beta. So this is minus 1. So this is n minus j, right? This is n minus j. Okay. This is just a notation. Okay. Just a notation. Okay. So we can see that this index and this index add together is n. Okay, is n. All right. Okay. So let's keep going. So then we write something, we can extend to infinity. The reason is because everything less than 0, it will be 0, right? So it's okay. We write this way. So it's okay to extend the 0 towards minus infinity. So this form, remember I write x k. This is xn, okay, xn. So j is like a time constant, time axis. J is like time axis, okay. So this is a signal uj. This is another signal, but this signal, according to the j, this is a minus j. This is kind of a time reversed, like time reversed. So instead of you write, so h1, h n minus 1. So when you do n minus j, then what's this? Okay, so this is a h n minus 1. Okay, then you get x1. So this is a original signal, but if you write n minus j, it becomes this way, right? So it's kind of reversed. Okay, reversed. Okay, so this actually is called discrete convolution of two signals, discrete convolution. So we are going to focus on this one next. So the reason we need this type of, so remember, this is my xn, actually xk, because this is k, right, xk. So because xk is this way, okay, is this way. So xkz minus k is xz, right, xz. So if I treat this as my uk going through a system that is xk. Okay. So inside here is actually a hk. So so we according to our definition here, we move the z minus k inside, because uj can be pulled out. So basically, we swapped this two sigma. Okay, we swap this two sigma. We do the j summation first, then do k, then we swapped that. So this is uj still here, and the others are just in here. Okay, just in here. Okay, so by doing that, we discover that this is a there is a k minus j. If I do z minus j and zj, so this is 1, right? Okay, so this one will get out in here because there's nothing to do with k. We can get out. We keep this one left, so it will be, sorry, it's z. Okay, so then we have z minus k plus j. Okay, but it's also equals to z minus k minus j. Because k minus j and k minus j, it is actually according to the definition, it's actually of z, definition of z transform. And here is nothing to do with j, so this is a uj. So you can see that it's a uz and hz. It becomes, if you have a z transform of uk, z transform of hk, and z transform of xk, you have xz. So it turns out that your output z transform is simple product of the input z transform plus multiplied by the hz. So hz in here is called impulse response of that. So this is corresponding to the continuous case. I have a ut, I have going through a LTI system g of h in here. So you have a yt. So the yt, okay, will become ut convolute with my gt, while my gt is inverse Laplace transform of gs. Okay, so why? Because this is a 1 input into g, so you get something called a Laplace transform of gt. So this is gt is called impulse response function of the whole system. So in transformation domain, then you have a y of s is u of s times g of s. But in time domain, it is ut convolute with gt. So that's why convolution is so important for our system response study. Okay. Okay. So from system point of view, okay, so we have difference equation. From this is difference equation. So then you have an input signal, any type of non-constant signal in here. So it's possible you can do a very simple way like this, okay? Very simple way like this. So you simply say, oh, my output xz will be a z minus 1 xz and b z minus 1 uz. So then this is actually the hz. So hz, okay? So this is a z transfer function is called. So z transfer function, okay? But you can also solve by recursively you solve. Oh, you express xn always in terms of initial condition plus all I instants. You can also arrive in here, okay? You also arrive in here, okay? So it's the same pathway, but obviously turning difference equation into z transform, it will become everything become what? Algebraic. So it's exactly the parallel to using Laplace transform solving differential equations. Okay. So let me hide this one. So solving differential equation using the Z transform, we have a universal tool in here. So you have output Z transform divided by input Z transform, you get a transfer function here. And the inverse of this one is the sequence. This one is called impulse response sequence because it's discrete points. Okay. So that's from system point of view. Okay. But how to do that in Matlab? Okay, we can go through some examples here. Okay, I'm going to run through this example with you next, but let's go through some examples here before we move on. Okay, so I'm going to show you some animations as well. Okay. So let's see. It's lots of text, but I already explained it to you. So the convolution, why this is very important, because it's very most important concept for electrical engineering, because this can decide what is your output signal for LTI system, if you are giving any type of input signal, and if you also know the system's unit impulse response. So you put a delta T unit impulse to the system, then you get GT, GT, right? And in Laplace transformation domain, so this is 1, so this is GS. So 1 times GS is GS, right? So, but for discrete time, we can do something very similar, okay? So it's like this, okay? So we are adding everything up for K. This K, one is positive, one is negative. The negative one means you reverse the sequence. So then you add this one together. So as I told you that, so you have Fk, so you have Fk, so you have an array of Fk. But if you have also a Gk, okay, Gk. Say for example, GK, you write something like 1, 3, 5, 7, okay? But if you write Gn minus K, you should write 7, 5, 3, 1, okay? So then you start to say, I have a K, so starting from very far away and start to move and keep this one fixed, okay? So you have it's like a train, okay? You stay there, okay? Then this train is going this way, so they are going to meet, okay? They are going to meet. Then you meet, you have overlapping. If we meet no overlapping, then this one times 0, this one times 0, so everything is 0, okay? Only when you have a meet, then it's non-zero, okay? We are going to see the animation soon. So why bother? Why bother? Discrete time convolution. So this is the reason, because discrete impulse, you do infinitely do this multiplication. So this is only when n equals k or k equals n. This is not 0. Otherwise, it's 0. So then you only have xn left. So this is called you pick up. You pick that specific point of X array. So this is also called sifting. You only have this one point left. You sift for the array. Just pick up that specific one by specifying which one you want. Oh, I want n, okay? So you can put n1, then this is n1, right? So Then you can do a linearity. You can say, oh, this is a xk. You have a this is an operator on this one. So say for example, you have x. You want to go through something called h. So then what you should do? Okay, what you should do. So it's okay because xk can be pulled out. Then h can move inside. So then this is operate on that. Operate on that. So h operate on that. That is basically a shifted unit in impulse for this one. Okay, for this one. So it's as if we're talking about you have h here, you have delta. So if we have a delta, you have n1 in here. So what you get is also h n1, right? So all shifting is you pick up that point. So now we have n minus k here. This is n minus k. So this is also n minus k. So I end up in here. Okay. So this is exactly our definition here. So it's x convoluted with h. So the output here, what's this? This is x convoluted with h. So that solves all the linear system response. Okay, so that's why bother we need to learn this convolution. Okay, so but in computer you actually can do the convolution. Okay, by using this command. It's a conv. A is an array, B is another array. Say for example, you have x, you have a h, so you want to get a y. So y equals x h. Okay, x convoluted with h. Then it's actually written as convoluted with x or h. You can also try this one as h versus x. And this one says also can be like polynomial multiplication. So you have a polynomial, you multiply by another polynomial. So what is the one? So I'm going to verify one thing for you. So this is like, I have a polynomial 1 plus x. Another one is a 1 plus x. So we know this is a 1, 2, 1, right? So you can see a 1, 2, 1. Okay, this is exactly true. So if I have, we do one more. So I convolute this one first, then convolute this. So it's 1, 2, 1 versus 1, 1, you get 1, 3, 3, 1. So everybody knows this triangle, right? So you do 4 times, okay? Then you get 1, 4, 6, 1, isn't it? Okay, but this is also the same. If you do 1, 2, 1 is an array and 1, 2, 1 is another array, 1, 4, 6, 1, this is the same. So this verifies that we can do a polynomial multiplication. Okay, so if you have 2 polynomials, you want to multiply them and you want to know what is the coefficient, you should use the convolution of the coefficient, that's discrete convolution. So I'm going to give you the first animation of this, okay? So this is a continuous convolution. You have seen this before, right? Okay, I'm going to pause. Say for example, you have this is the L because this is your this is your what they called actually this is called support. Okay, support L1. So this support, the after convolution, the support will be L1 plus L2 minus 1. Okay. Okay. So how many points in here? So this is an example. Here's another example. So remember, Hn is already reversed. So you have 5 samples of Hn. But Xn, they don't have to be the same length, okay? So the total one will be 11, right? So 7 plus 5 minus 1 is 11 samples of the results. So because the overlapping is different, so this is one example. This is another example, okay? So you think about this is like 2 trains, you cross it. So you count the summation, then only when they start to intersect, okay? Once you get out, it's 0. Okay. Anything beyond this is 0. So you can. So I'm going to repeat this one using conv. So this is an array. This is another array. Remember, we started at 2, 4, 6, 3, 0. Okay. That's the H array. This is already reversed. Okay. Remember, it's 2, 4, 6, 3, 0. Okay. Then the result is like starting from 0, end with 0, and you have 6, 10, 18, and last is 12. Okay. So I'm going to do that. So this is a 2, 4, 6, 3, 0. Okay. So this is the real H. After reversed, it's like this showing in the movie, in the video, right? So then this is a 2, 4, 6, 3, 0 is my H. X is like I copied that, so it's exactly like this. So I convolute X, comma H. So then I got this one 0, 6, 10, and last one is 0 here, and here's 12. So it is true. If I swap the position H, comma X here, you can see we give the same results. So we verify that. Okay. So let us come into here to see. So you can see add one by one. Okay, add all those sigma, all those things together. So this is how discrete works. So let us review animation of convolution of 2 times signals. So this is actually a continuous time. So we're going to watch. So this is a cartoon I showed you before. At that time, probably you have very vague definition of convolution. So indeed, it's worldwide. People protest in the deans of engineering office, down with convolution. Convolution stinks. I hope after this class, you feel convolution is more beautiful and useful. So the spark is worse than spike. I think the meaning of this one says it's not so hard, not so painful to learn. It just sounds like hard. Okay, so let's continue. Okay. Oh wait. So I like this cartoon. Very nice. Okay. So if I have 2 boxes, one is 0 to 2, 0 to 1. So the final one is a 0 to 3. Okay. Because you start from here, non-zero, and going up. Then it's always the same. Can you see? When you move here, it's always the same. The area is always the same. You multiply because all others are 0 in this dashed box. So then it's still same until here. Then you shift over, then this is 0. So then it's going down, okay? Going down, down, down until to 3. So you can see one signal support is 2, another signal support is 1. So together the support will be 1 plus 2. 2 plus 1 is 3. So after that, they will be totally separate, no intersections, everything will be 0. That makes sense? Okay. So this is from Wikipedia. There's a dedicated convolution one. This is a faster animation. So you have a f, a g minus t tau, f tau, then this convolution. So the black one is the convolution. So you can see one is from minus 0.5 to 0.5. Another one is actually the same, okay? So then it will be minus 1 to positive 1, okay? The support will enlarge like that way. So I think this will help you to understand the convolution much better. Especially mostly useful is the discrete time is also useful where you solve the 2 polynomials. So you multiply 2 polynomials, like you have many terms, you do manual expansion is tedious, okay? But using convolution, that will be straightforward, okay? So let's having fun on this, and then we come back to our real work, okay? Now let's face our reality. So I have a real system. We derive this water tank system. So this is nothing but to me, you have a z minus b. So a and b are just constants, okay? Constants. So although we derived from continuous time equation, so we end up with this, but don't worry. So we just think about this way. So because we discretized from a continuous time system, then we discretize it. Suppose we have x dot is xk minus 1 divided by ts, okay? So this is actually approximately equal, okay? So, but anyway, we end with, well, our starting point here is, first of all, the difference equation. So you treat all these things as just constants, okay? Constants, okay? Now I have input is this, I gave you this, what is output? So according to what we have learned is, I'm going to, this is a difference equation. I do z transform. So this is +1 is a z, yz. This is a yk corresponding yz. This is a copy, right? This is a copy. So this is uz. So then I put this one to this side. I'm going to have z, this one. Then I have this one here and with uz. So you can see this is nothing but my hz, right? This is my transfer function, okay? Transfer function, hz. So this is my hz, right? Hz. Okay. The same thing is here. The hz, I copy the hz is here. Then uz here is this guy. Okay, this is my uz. Okay. So this is multiplied together. So now this is a critical step. We need to find yk. We need to do inverse. Yk is a z inverse of inverse z transform of y z, so equals yk. So that inverse, if you do a definition, is hard. How to avoid that? Okay, so what you do is to split this multiplication into summation or subtraction. So this process actually is PFE. What stands for? Called partial fraction expansion. And you should know this thing immediately. We taught you some of the ideas like copy, okay? How to do PFE. Well, we also use some identities. You can do that. So then after the PFE, you got this one. Okay, you got this one. All right. Okay. So actually the PFE is simple. Say for example, what is this? How this is decided? Easy. You want to do z minus 1's coefficient. You cover z minus 1. You cover this guy. Cover up. Cover up. Plug in what? Plug in z is 1. So z is 1, you put it here. Z is 1, you put it here. And this term will cancel. So what's left is b divided by a. So copy still applies, okay? And plug in z is 1, okay? Same idea, okay? And this is also true. You can do the copy. Okay, it's gonna be cover this guy and insert that, so you'll get this. Now, with this one, you can use Z transformation table. In the final exam, we will give you Z transformation table, okay? We have that one in our textbook, okay? So if you know that this is B divided by A, this is just a 1, okay? Just a 1. And here is exponential here. This is lambda, right? So this factor to the power of K, okay? Okay, so you can see now we can solve first order step response in discrete time domain via the Z transform. We didn't do those kind of by enumeration, very complicated method, right? So don't you guys feel proud of yourself? Yes, you should. Now, let me remove this. So I think in the next 2 slides, I need to remove this one, okay? It's okay here. No, I keep it here. So what's next is going to talk about some basic Z transformations. Say, for example, that I have a S, one of S, this is called integrator, okay? And this is called differentiator, right? So I want to understand what is the discrete form of that? We already roughly know one of S is like Z over Z minus 1, okay? We already know that, but how this was discussed. So we know this one, okay? We know this one. So now I'm going to study with you. So if I put the impulse response in here, what's going to happen in here? So this is a step, right? So if you put the impulse in here, so you get impulse dot. I don't know how to say that. So it's hard to imagine then, okay? What impulse transfer function of a differentiator. Let's try to understand what's going on. Say, for example, I have a room temperature. So basically I say, oh, I have a theta in here going through some secret block. I come out as theta dot ddt, right? So I want to understand what is the impulse response of hk of this thing. Let's try to derive, okay? So let's assume that theta dot, this is theta dot is y, is denoted as y, okay? So then y is basically a theta dot. Then how to express y in terms of theta? Then we can do k plus 1 and k and divide by ts. So this is a finite difference approximation of that. So this actually should be approximate. So this is good. And then when we do sample, so this is the current one, this is a next sample, nothing in between, okay? Nothing in between. In between t and t plus ts, there's nothing there because this is all the dots, okay? All the dots. So this is, okay, we know that. So now let's write it in terms of, because I know that ddt is considered as y. So y is output, theta is input, okay? Theta is input, y is output, okay? So I have a theta t theta z. So plus then is a z theta. So this one, so y divided by theta, this is in, this is out. So this is in, this is out. So out divided by in is my transfer function. So this is my transfer function of what? Of a differentiator, right? Differentiator. So differentiator, so what do we say differentiator? Differentiator basically is when the k is this one, so this is 1, and here's z and ts, okay. I think this is not so hard to understand, right? This is our beginning point, okay? How about the integration? Integration is the same. So if I add a time step in here, so I do 0 to t integration and t to t and s in here. So this is like I have theta as an input going through some secret block, and I got the yt, which is integration of my theta. So this is just the integration. Again, I want to understand what is hk, what is hz, what is that? So it turns out that we can derive this way. So we treat yt, this one here. This is a yk, yt, this is a yt. So it's a yt and this one. I will assume that in this ts is so small, the theta is constant. Okay, so something like this. So this is a k, this is a t plus ts. So this is so small, ts is so small, that these two is approximately the same as the theta t. So this is my theta t. Okay, so I didn't change anything. Theta t is a constant, then times the ts is this triangle approximation. Okay, triangle approximation. But some may argue, hey, how about I do this triangle? Yeah, sure, you can also do that. Okay, this is using this one as a constant triangle. Okay, sure, you can do that. So if we do transformation here, you have a z, this is a z, okay, yz, you have a yz in here, then this term is theta z. So therefore, for integration, I got this one. This is my hz. And do you see something different? So if I consider this one, so z, yz is this term, yz is this term, and ts and z, theta z is this term. Okay? So I arrange then this one to this side, the z minus 1 here, y, and here is a ts z. So I divide it by z, so I'm going to have this one. So this is called backward versus forward. So this is the forward, this is backward, okay? Backward, so this is forward. So it's a little bit different. What's the difference? I think you should compare these two, and this difference is the z. That makes sense. You just shift one step difference. Okay, no big deal, right? I think so. Yeah, I think so. So this is a pictorial view. I'm showing you that. So if you use, so this is like this is called forward. This is called backward. So this is this form. So the only difference is the z term in here. Okay. And remember, this is from k versus k plus 1. All this is corresponding t versus t plus ts. Okay. So this width is ts. Okay. So how to represent the shaded area? But the question you immediately can ask is, well, this representation is crude. What about I use a trapezoid like this one? How about this? Yes, people are thinking about this. So let's do another way on trapezoid. So this trapezoid is also called bilinear formula. So basically, I'm adding these two terms together, divided by 2. Okay, divided by 2. So basically, I add these two together, divided by 2. Okay, so I'm doing something in between, right? So divided, but that's why we divided by 2. Okay, divided by 2. So basically, I'm doing this. I'm adding this equation and this equation add together. Okay, add together, you got this one. Okay, you got this one. So this one will be more accurate in the sense that your y divided by q, theta, sorry, that's it. Then it becomes z plus 1 divided by z minus 1. So you have ts divided by 2. Then you can also write it in this form. So you can see I start to prefer using z minus 1. Okay, there's a reason for that. There's a reason for that. Z minus 1, that means suppose t is your current moment. You use yt, it's okay. You measure that, you use it. Then t will go further. So that's the future. So future, say for example, t plus ts. That's the future information. You don't have it yet. You are not a fortune teller. So it's always useful. You want to take action, you should use the current information and previous information. Okay. You are not going to use future information. It's not available to you yet. Okay. So if you use future information, that's called non-causal. Okay, non-causal. So that's the consequence of the course. And the course used already consequence. That doesn't sound right. So it's called non-causal. So Z is non-causal, okay? Z minus 1 is causal. So Z minus 1 times any of this current signal is minus is previous information. So it's causal. So I prefer to, so although these two equations are all correct, but I prefer this one. You always use Z minus 1. So some of the people never use this one. They actually use a Z minus 1, or transfer function is Z minus 1. They use Z minus 1 instead of Z. I think that makes sense. Okay. All right. So let us review what we have learned so far. We talked about difference equation, Z transform, inverse Z transform. This is a basic lookup table, okay? We focus more on the one-sided because in the reality we use starting from 0. Talk about the properties and IVT, FVT, and time shifting. And we'll talk about path transformation, like convolution of discrete. And also we have a byproduct. We know how to do polynomial production, okay? I verified the triangle table for you, right? So, but all these things is based on that you have T of S, you already sampled this. You have signal, you already sampled, okay, continuous time. Then you sample the discrete time, you have those dots, okay? Okay. And we explain about the opposite of this H, then you do this. So it's H convoluted with U, okay? But of course, it's also a U convoluted with H. So we talked about those already. So we are going to do a very important topic today. It's called sampling. So the TS is called sampling frequency or sampling period. 1 over TS is called FS, it's a sampling period, okay, sampling period. So I already alerted you in the beginning. So this is the very important parameter you need to decide in the early stage, very beginning, like, oh, how fast I should sample. If you sample unnecessarily fast, you pay extra price for those high-speed sampling circuits without actual much gain. But if you sample slower than needed, okay, slower than needed, then there are some bad consequences about it. So all these things we discussed so far, we haven't focused on about this question about how to sample and how fast we should sample. What is the governing theorem behind it, known as sampling theorem. So the sampling in last year, we are in 12b and it's 10th. So I feel like we are synchronized to last year's offering. I didn't erase this one. That's great. That's great. So we need to answer the questions how fast we should sample. And when you do the sampling, I said you have a signal and you only pick up all those points, right? Okay, all pick up the sample, you pick up those points. So what's lost in between? Okay, what's lost in the in between? And how we view this in the frequency response point of view. Okay, and in a nutshell, if you have something in S domain, how you can get into the Z domain. So say for example, you have G of S, how you can, so you have a TS in here, okay, sampling period. Then you should have a Z in here. How you can get that, okay? And the bad side, something called aliasing. What's that? How bad it is, okay? And how to avoid it, okay? So all these questions we must answer in the next 25 minutes, okay? So let's visually see the consequence. So these are the sampling points you have. So you may feel like, oh, what's the original system? So we are trying to infer or reconstruct what's the original continuous time signal, giving the discrete time signal. So visually, you may think about, yeah, it's a constant line, but this is only one possibility. Could be like this, okay? So now the question is, yes, I pass all the points, but my original one is, so this is actually because of not sampling fast enough. So therefore, you cannot go back and reconstruct the original continuous time signal like this zigzag line, okay? So the reconstruction in this case is not possible because of the slower sampling than needed. So, but in advance, how do I know I'm not sampling fast enough? Okay, so good question. We are going to answer this question. I think it's okay. We can tolerate this slide because we are reviewing this the delta function. We know the delta function is a generalized function. It has a shifting property. Shifting property. So what's the shifting property? That is, so if you f, then you do delta t minus t0, you only have this one, t0 left. So in other words, if I want to pick up a point in ft in this t0, what should I do? Mathematically, what I should do is I put this ft and delta t minus t0, then I minus infinity to positive infinity. This one will give me ft0. So it give me a curve ft, okay? Give me a curve ft. I only have this 1 point left, okay? So I pick that specific point. Yeah, I'm doing the same in here. So I'm doing the same point in here. So this is called a shifting property, okay? Shifting property. So if I know how to pick up 1 point, I know how to pick up many points. Say for example, I have a capital T is my sampling period. So I just many of the sampling points. So so I just line all these pulse trends. So it's a sigma of this thing. Then I convolute with my f. So what's left are just all these, pick up all these points, okay? So this is as if we did the sampling. It's called discrete time sampled. So the sampled signal here is called f star, f star. So f star is the sampled points of f of t. So there are nothing in between, okay? The black line is not there. There's no black line. So this is the original f of t. But f star t is only those dots, okay? Only those dots. Okay, only these dots. So in a nutshell, the sampling process is like you put this pulse string there. I would like also call this is like if you comp your here in the morning, look at those T's, right? So this is like comp. So you comp the signal, you get what you have. So this shifting property, we already reviewed it. If you need this point, you can pick up it. So it's a generalized function, delta t, and this definition is integration of this thing is 0. So basically you call it has a 0 width with infinite height, okay? So this is called impulse, okay, impulse. So Laplace transform impulse is 1. So this is just a review, you know it. So what is the impulse response function? Because this one you multiply by 1 in here. The 1 is input, GS is the system. Output will be y of s. Then you inverse Laplace transform, you get a yt. The yt is also called gt. So it's called impulse response. Okay. So it's something like this. You have g of s, you get a delta t in here. What's output? Output is gt. It's impulse response. Now I say that you have the same system. I'm going to have u of t in here arbitrary. Then my output is y. So then what is y? Y is u convoluted with g. That's simple, right? Or you can say y of s is u of s times g of s, okay? And the convolution law in Laplace transformation property list is exactly the same. So if you have two functions convolute each other, then in the transformed domain is their product. Okay. All right, this is a critical slide. I want to refresh this one with you. So we are going to study this Laplace transformation of this. So remember the f star is the sampled. So remember we talked about it. I lost something here. Okay. So list 2 slides, and the next one is this next 3 slides are very important for today. So you may feel these are all the math, but you should feel proud of yourself that you can explain them in the future. Okay. So here's why. Okay. So we try to understand. Okay. So I told you that you have a FT going through some COM filter pulse. These are delta t minus k, capital T. So you go through this pulse. This is called a sampling process. Then you are going to get FT, right? So the FT is, so this is my f of t. So this is actually is all the points, nothing in between. So I'm just superimposed on this. So these are the dots, okay? These are just the dots. If you want, you can write some pulse in here. You can write something like that, but that's not necessary, okay? So just know this is a picture. So you know that this one has f of s, okay? F of s. I want to understand what is my f star s, okay? Simple, simple. We just pull out this signal here, put into the definition. This is this definition, right? This is a definition. All right, definition. But remember, this f star is actually, according to this picture, is original function going through a okay, yeah, convoluted with this shifted taus. Okay, it's from minus infinity to infinity. Okay, so this is a convolution. Okay, this is a convolution. All right, so after that, we know that so this value is 0 if tau is not kt. So then I just write fkt. Otherwise, it is simply not going to. So the tau is changing, okay? Tau is changing. So this whole integration makes no sense, okay? Because you change the tau, everything will be 0 only when tau equals kt. So tau equals kt, this is not 0, delta is not 0. So this fkt is like this, okay? And same thing, the tau has to be equals kt. Otherwise, everything is 0, okay? Okay, so that's true. Then we have this one left, sk here. So this expression is what we call f star s. So this is f star s. We got that. So we are trying to reconstruct from here to here. We are trying to see what's going on, okay? So fkt is all those dots. So it's a discrete dots, okay? Discrete dots. Those are the fkt's, okay? So those are the discrete sequence of f, okay? But if I do e to the st and to the minus kt, this should give me fz, okay? If I choose this guy is z. So the Laplace transform of sampled signal should give me fz if z equals this one. So in fact, this is the exact zs relationship, okay? Zs relationship. T is a sampling period, okay? T is sampling period. So this is the exact zs relationship, okay? All right, okay. So this is strange. This is strange. Previously, so we did S is something like Z minus 1 divided by T. Remember the differentiator? So this is strange. Okay. I would like to say this is not. Okay, it is not so strange. Okay. So we are going to see. So this is exact, and this can do approximation for that. Okay, approximation for that. Let's try and see. Let's try and see. Remember, e to the power of x is 1 plus x plus da da da. If we cancel everything, then we have x in here, right? X is small. So in fact, z could be written as simple 1 plus st. Do you see that? Do you see that? Approximated, okay? Approximated. And this one will give you this equation, isn't it? right? So this is just the first order truncation of the Taylor series expansion. Okay, so the dots are being connected. So that's everything we understand regarding the sampling from a Laplace transform point of view. The next one is to do an explanation in Fourier transformation domain. So first of all, we have learned what is a Fourier series expansion. Fourier series expansion. Because this Pau strand is considered periodic, okay, periodic. So its Fourier series exists, okay, exists. So then this delta, this sequence, these are those periodical infinity series can be written in terms of Fourier series expansion and written in this way. Okay, written in this way. So this is actually according to Fourier transformations. So this is a cosine sine. So do you still remember? So Ej theta is cosine theta plus j sine theta. So you can write in this exponential form, and you can get this out. So n is moving from minus infinity to positive infinity. So 2 pi divided by t is actually omega, okay? So basically this is like j omega n t, j omega n t. So then if you say this is omega 0, okay? So then it's omega 0. So then it be a cosine n omega 0 t. So this is just the high order harmonics, okay? So this kind of thing, I think, is in the definition of those Fourier series expansion using this compact notation here. Compact notation here. So let us study again. So let us study this one again. So this is a sampled data, sampled signal for f of t continuous time. Then we study Laplace transform. Okay. But now we know that this f star is of f times this series expansion. This one inserted to replace this sigma. Then this is still here. Okay. So we are doing this. This is a delta. This is a sigma. This one is this term. Okay. So then we represent in the Fourier series expansion. So we write this one in so you can see here you have a e. So copy here. So what is this one? So what is this one? Let's swap again. We do a trick. Swap the sigma and integration. Okay, you swap these two. Okay, so we are getting to here and here and here. Okay, so this is not changed. So we only have this one changed. Okay, so n will still sum like this one, but inside in here is something very different. Okay, it's very different. So I want to express my f star s in terms of fs. Okay, in terms of fs. Fs is because of Laplace transformation pair of original signal ft. So by doing that, we find out there are infinite many terms. Okay, infinite many terms. If we introduce, so this is, let me see. So this is the integration here, and this is this one. So we can consider this is a Laplace transformation variable shifted, this term. So in other words, originally I have f of s. Then after sampling, my S transformation will become infinite number of terms in here, okay? infinite many terms in original. So remember F and F capital is a Laplace transformation pair, okay? But this is actually my F star S. It's a transformed the sampled signal. So this has a huge implications like this. Remember, you place S is j omega there, you are going to get a spectrum. So this is a spectrum. So the shaded area is your F j omega. So this frequency domain. So F, so you have Ft, you have F of S, and also you do Fourier transformation, you have F j omega. Well, basically, this is basically S is j omega, you get this one. So this is my magnitude. Usually you do a 20 log 10, okay? So that you can see the signal has a shaded area. So this is like a spectrum because your frequency is in hertz, is a radian per second, okay? So we call this signal a band limited signal, okay? Meaning at certain frequency B, then everything will be zero, okay? Will be zero. So the energy are mainly focused in here. The reason we have a symmetric imaginary frequency is because of the math reason, mathematical reason, because we have this n, okay, goes from infinity, minus infinity to infinity. So let's focus on this case. So for example, if you have only a sinusoid, so you only have a omega 0, sine omega 0 t, sine omega 0 t. So then this is the omega, you have a bar in here, okay? So this is 1, okay? Okay, so everything inside here is a band limited signal, meaning you have frequency cornering here, get to the 0. This is usually true in practice, usually true. Okay, so that's before we do the sampling, okay? But after we have, so we put this continuous time signal, after we sampled, we are going to see that this shaded area will get duplicated with many copies, infinite number of copies. And the center frequency from 0 to, this is omega s, the sampling frequencies is 2 pi divided by t, okay? The sampling frequency, omega. So you have 1 omega, 2 omega, 3 omega, infinite, okay? This is, okay, 2 pi divided by t, yeah, it's here, okay? And this is the B, this is the B. So that's because of this equation, okay? This is because of, this is called spectrum duplication. So one of the ideas is, if you only have a single term sinusoid and you start to sample them, then you do Laplace transform of the sampled points, the signal. Then how many turns, how many frequencies? You have infinitely many frequencies, okay? So this is your omega 0, this is sine omega 0 t, so this is omega 0. So then you also have omega 0 in here. You need to shift this one, so you plus omega s. So this is omega 0 plus 2 omega s, the omega 0 plus 3 omega s. See what I mean? So you get duplicated infinite many copies. So for continuous time signal, you only have one frequency. But after sampling, you have infinitely many frequencies. Okay, so that's the difference between sampled data signal versus continuous time signal. I think we stop here, and next time we are going to start with sampling theorem. And we don't want to go so far. I want to have everybody have a very solid understanding about the sampling process. And don't worry about this math derivation here. If you are not feeling comfortable about this part, about this step, you don't need to worry. Okay, you don't need to worry. But you understand it has a math interpretation. So this is just a graphical representation for you. Okay. All right. We stop here. Next, we are going to start with sampling theorem and the aliasing and anti-aliasing problems. So we stop here. So we have almost a little bit more than half students in the class. What's the reason? Perhaps everybody's tired of Zoom, huh? And this is no good. I don't feel good. So I don't believe half of the class always got something cannot attend. This is not a good sign, okay? That's not a good sign. So then I want to say that if in the end you don't do exam very well, you should not blame me. You should blame yourself, didn't try to synchronize the class. In myself, I watch, it's okay I watch and Zoom, recorded Zoom lecture, but it's different, okay, it's different. I open my video, you can see my face, you can see my tone, it's a little bit different. So I still strongly suggest everybody attend the class in synchronous way. All right, so the quiz is already in the system. Enjoy that. I'll see you next Wednesday. Have a good weekend. Be safe. All right, bye-bye.